Welcome to this explainer. Today, we're doing a deep dive into river-suspended sediment transport, and we're stepping way beyond the macroscopic diffusion models that have dominated river engineering for decades. We're going to jump straight into the physics of microscopic particle mechanics, focusing heavily on velocity gradients. Because as we know, suspended sediment isn't just some apparent phenomenon smoothly diffusing through water. It's the product of incredibly precise local mechanical interactions right at the particle level. So let's dive into this paradigm shift and see exactly how it works.
Okay, let's take a quick look at our roadmap for this explainer. We'll start with the limitations of conventional theory, move into velocity gradients and upward forces, and then discuss moving beyond intuitive interpretation. After that, we'll cover 3 specific verification approaches and wrap up with how we're advancing practical models.
Starting with Section 1, the limitations of conventional theory. We all acknowledge the utility of standard classical concentration profile models, but we really need to pivot to their explicit physical limitations.
That traditional balance between downward settling velocity and upward turbulent diffusion gave us a really useful mathematical framework. But let's be honest, the physical cracks are beginning to show, especially in dynamic, real-world river systems. Moving from that old average field assumption to the actual physical realities of the new microview represents a massive paradigm shift. Conventional models are great at predicting mean concentration distributions by treating turbulence like a giant blending machine. But that assumption inherently masks the localized, instantaneous forces that are actually required to lift a particle off the riverbed. It doesn't tell us the how or the why.
So here's the core issue. While the conventional model works fine for steady, uniform states, treating upward movement as a complete black box of diffusion creates a massive predictive bottleneck. I mean, it relies entirely on empirical data just to set reference concentrations near the bed. Plus, settling velocities aren't constant. They fluctuate thanks to cohesive fine sediments and high-concentration particle interactions. But the biggest limitation, this macroscopic view completely ignores explicit shear-induced lift forces. Think about a sudden flood rise. In those non-equilibrium states, that black box just completely fails to capture the true mechanics. Which brings us to Section 2, velocity gradients and upward forces.
Let's actually unpack that black box. Instead of just waving our hands and calling upward movement diffusion, we need to meticulously isolate the specific physical parameters governing a single particle's motion. We're talking true two-phase mechanics here. Transport has to be evaluated through the precise sum of gravity, buoyancy, drag, and, this is absolutely crucial, shear-induced lift, pressure gradients, and turbulent fluctuations. It forces us to treat the sediment and the water as 2 distinct, actively interacting phases.
Picture what's happening right at the riverbed. Because particles have their own inertia and settling velocity, they don't just perfectly follow the fluid flow. This creates a relative motion. When that relative motion intersects with the steep vertical velocity gradient, where water is moving much faster just slightly above the bed, it generates a direct upward shear-induced lift force acting precisely perpendicular to the flow. This exact mechanical force is what initiates suspension, and it is especially dominant when we're dealing with fine sediments.
And the complexity doesn't stop there. Once a particle is actually lifted from the bed, it's not kept in suspension by some smooth, uniform diffusion. No, it's sustained by violent, instantaneous turbulent structures. We're talking about coherent turbulence here. Ejections transport low-speed fluid masses violently upwards, while sweeps push high-speed masses downwards. Fine sediments are incredibly responsive to these intense vertical velocity events, so rather than a smooth hover, particles are continuously cycling through sinking and rising via these highly energetic turbulent bursts.
Let's move on to Section 3, moving beyond intuitive interpretation. We need to address a really common misconception in fluid dynamics. We've all heard the overly simplistic explanation, right? Fast flow equals low pressure, so particles just get sucked up. Well, actually, scratch that. We have to translate that loose intuition into rigorous particle mechanics. Upward transport is definitively not a static vacuum effect sucking particles up from the riverbed. It's a dynamic, localized interaction of shear-induced lift, pressure gradients, and coherent turbulent ejections. Getting away from that simplistic analogy is absolutely necessary for accurate modeling.
Now, I want to deeply emphasize this highly nuanced point from the source material. We are not throwing classical equilibrium theories in the trash. They are still foundational. What we are doing is supplementing the physics hidden behind that convenient turbulent diffusion term. We're giving these models a high-resolution, mechanistic backbone. and finally bringing exact mathematical clarity to what that diffusion term actually represents mechanically.
Okay, Section 4, 3 verification approaches. How do we transition this from a hypothesis to proven science?
The source outlines a really elegant, three-pronged methodological blueprint to isolate variables that normally happen all at once. It's a clear logical progression. First, controlled Flume experiments using advanced particle image velocimetry to capture those local velocity gradients and track individual trajectories. Second, field observations utilizing acoustic Doppler profilers to capture real-world, non-equilibrium transport during actual floods. And third, rigorous numerical analysis using large eddy simulation and computational fluid dynamics. And as experts, you know exactly why LES is needed here. Unlike standard RANS models that just average out all the fluctuations, LES explicitly resolves the large-scale turbulent eddies responsible for those instantaneous ejections. That allows us to theoretically isolate the specific forces on the particles.
The beauty of this approach is how the steps interlock. Flume experiments will literally correlate particle rise frequency directly with actual ejection events. Out in the field, observations will track concentration peak heights when flows are completely out of equilibrium. But perhaps the most exciting part? The simulations will compare models with and without the shear-induced lift term turned on. That allows us to quantify its exact contribution to suspension over traditional average diffusion. It's brilliant.
Finally, Section 5, Advancing Practical Models. Because at the end of the day, all this theory only matters if it works in the field.
So, how do we translate these microscopic discoveries into macroscopic engineering tools? By dynamically correcting the diffusion coefficient. We inject these specific micro-level parameters, local velocity gradients, the Stokes number to precisely account for particle response time, and the exact frequency of turbulent ejections, straight into standard transport calculations. This isn't just some minor, incremental update. It's a game changer for accurately predicting complex, real-world issues like flood turbidity, riverbed variation, and non-equilibrium reservoir sedimentation.
To wrap up this explainer, I want to leave you with this provocative thought. Unpacking this black box is so much more than an academic exercise. Think about it. If we replace apparent diffusion with exact particle forces, how does that reshape our predictive models for coastal sediment supply? How does it change the way we preserve aquatic ecosystems? Mastering the non-equilibrium realities of our river systems starts right here. The exact physics matter, and they are completely changing the paradigm. Thanks for joining me on this one.